Hey guys, Matthew here, giving you a walkthrough on the week one worksheet of question 1.4, where we are going to prove that the sum of the squares given by this this statement, where the sum of from the first number to the nth number of all of those squares is equal to n times n plus 1 times 2n plus 1 all over 6. So when we have a problem like this, we first think of what proof technique do we want to use? And looking at this problem, we want to prove that this statement holds from the first number all the way up to some nth number. So as we want to prove that it holds up to some arbitrary n, we're probably going to want to use induction, as using induction can help us prove statements all the way up to um, some nth number. So now we are going to, as we know it's induction, the first step of inductive type problems is to start with our base case, where in this problem it's kind of given to us as we want to prove that um, the sum of squares from the first number to the nth number is um, is this thing on the right. So our base case in this case is going to be 1. And let's verify that now, where we have putting 1 in for n. We have 1 times 2 times 3 all over 6. 6 over 6 is 1. And we think about 1 squared being 1. That looks right. I think we should proceed. So now we move on to our inductive hypothesis. Now, our inductive hypothesis would be that this statement holds for up to some arbitrary number k. So we say that where n is k, the sum of squares for 1 up to some k is equal to k times k plus 1 times 2k plus 1 all over 6. Now, you may be thinking, okay, I know this is an induction problem. Do I want to use weak induction or do I want to use strong induction? And in this case, this is a problem where we're going to want to use weak induction, not strong induction. Because with weak induction, we can prove here, right? We're trying to prove the k, implying the k plus 1th case. And just kind of thinking, if we want to prove, our overall goal is to prove 1 to the k, or 1 to n. Proving the k to k plus 1 case will prove 1 to 2, and it'll prove 2 to 3, it'll prove 3 to 4, and so on, all the way up to say k plus 1, or k to k plus 1, which you can also say proves n minus 1 up to n. It just, this k to k plus 1 will always prove one number below proves one number above. And it's kind of like a chain of dominoes, as 1 implies 2. And then knowing that 2 holds, 2 implies 3, 3 implies 4. 1 implies 2, 2 implies 3, 3 implies 4. And it's kind of like a domino effect all the way up to our desired number n. And we can see that this alone is enough to prove this, what the statement we're going to prove holds. And so we're not going to need strong induction for this problem. So with that out of the way, let's move into our inductive step. So we're going to want to prove that this holds for the k plus 1th case, which would be from 1 to some k plus 1th number. The sum of those squares is k plus 1 times k plus 2 times 2k plus 3 all over 6. Now, when we see something like this, right, we're going to want to we're going to want to use our inductive hypothesis to prove our inductive steps. So then the question naturally becomes, how do we do that? How do we get our inductive hypothesis to work for us here? And we would do that by realizing, or by really seeing that the sum from the sum of squares from the first number to the k plus 1th number can be split up. So we're going to want to split up our sum of squares from the first number to the k plus 1th number into the sum from the first number up to the kth number plus the k plus 1th number squared. And what's nice about this is we know that this holds true by our inductive hypothesis, and now we can use that. So from our inductive hypothesis, we can fill this in, which we know to be k times k plus 1 times 2k plus 1 all over 6. And we have k plus 1 squared, which we're going to want to add in. And we can do that by giving it a common denominator. Then we're going to just want to add it in. And you see here that we have a k plus 1 squared here and a k here, so we can do a little bit of factoring. And then we can do a little bit of distribution with the inside parts on the right that we've factored. I'll show you guys what that looks like. K plus 1, which is factored on the outside. Distributing our k there, that'll get us 2k squared plus k. And distributing 6, 6k plus 6 all over 6. And then we combine like terms. And we see we have 2k squared plus 7k plus 6 all over 6. And here we see that this is also factorable. And this can be factored into, we're going to have 2 there. We got all things add to 6, then multiply to 6. And then 4 plus 3 is 7. So we can do, one factor will be 2k plus 3, as we need 4, and then k plus 2. And that is equal to 2k squared plus 7k plus 6. But we didn't really even need to do that factoring because in the problem they gave us little hints. And that hint was that 2k squared plus 7k plus 6 is equal to 2k plus 2 times 2k plus 3. So they kind of told us that those are its factors. But now we have k plus 1 times k plus 2 times 2k plus 3 over 6. And we wanted to prove that the reductive step, the sum from 1 to k plus 1, the sum of those squares is k plus 1 times k plus 2 times 2k plus 3 over 6. And what do you know? We have proved that the sum from 1 to k plus 1, the sum of those squares is, in fact, k plus 1 times k plus 2 times 2k plus 3 all over 6. And that's question 1.4 for you. See you guys next week.